Hey everyone, so in this video we're gonna go over chapter 7, multiple linear regression. This chapter is an important extension to the previous chapters, number 6. If you think about the model we learned in chapter 6, you would realize that the model is actually very limited, or you might actually question what if for the y variable there are several x variables that can be related to the y variable. And I can easily give many examples showing you that in most of the situations, it's hardly for us to find a situation where the y variable only depends on one x variable. Whatever you think about income, education, or any other variables you can think of, most likely there are more than one x variables that can affect y. So that's why we're looking at this chapter. We're looking at a situation where we have one y variable, one dependent variable, but several independent variables, several x's. So let's get started. Okay, so specifically, this is how the model looks like. And we do have a model for the population. When we use data to estimate model, which means we use data to find out values for beta 0, beta 1, beta 2, etc., we can get the regression line for the sample, and then we can use that regression line to do forecast. Okay, so let's take a look at the population model first. Y is still our dependent variable, depends on a couple of x's. X1, X2, until all the way to Xk are the independent variables. You can see this is K here, meaning that it depends on the situation. Sometimes you have 3 axes, sometimes you have 5 axes, and sometimes you even have 10 axes. Now, you notice that for each x, there is a beta associated with it, right? So beta 1 x1 means beta 1 here is the coefficient for x1. Now, in simple linear regression model, we call beta 1 the slope coefficient. In multiple linear regression model, although we can't use the scatter plot to represent all the data there, we can still call this beta 1, beta 2, until beta k the slope coefficient. And beta 1 actually kind of measures the relationship between y and x1. Same for beta 2, measures the relationship between y and x2, although we will not call beta 1, beta 2, beta k the correlation coefficient. They are not exactly the same as the slope coefficient. And then going back to the beginning, beta 0 is the intercept. Same idea when all x variables take a value of 0, the value of y is equal to beta 0. And lastly, you will see the old error variable, which we saw in simple linear regression model, that measures the difference between the actual y and the estimated y using our model. So to a certain extent, this error variable really measures how well we can forecast for using the model for the data. It measures what's the actual value versus what we can estimate using our model. Of course, the smaller the error, the better our model can do the forecasting job. Okay, now suppose we collect data on y and all the axes, and we use, as of for now, we use Minitab to estimate the model, meaning we're trying to find out the values of beta 0, beta 1, etc., beta k, that can best represent the data. Then, with that estimation, we can come up with this sample line, which is y hat, which is the estimate y equal to b0, which is an estimate of beta 0 using the model, plus b1, an estimate for beta 1 using the data, times x1, plus similar terms until the last x variable out there. Without going into more theories, let's take a look at an example and really learn how we start from being given the situation, estimate the model, check the model, and use the model to do forecasting. All right, so here's the example. It follows the one we had in chapter 6. So it says, in the example of Mr. Bump, the R squared is 75%, meaning he can explain about 75% of the differences in gallons of milk sold by using price. To do a more accurate job of forecasting, he needs to find other variables that will enable him to explain the rest of the variation. Mr. Bump decides that advertising expense might help improve his forecast of weekly sales volume. So what we see here is, continuing from the example we had in chapter 6, Mr. Bump was looking at the relationship between the price of milk versus the amount of milk sold. And we know that the higher the price, the lower the amount you can sell. But that only explains 75% of the variation in purchase, the sales. And to improve his model, he decided to use another variable, which is the advertising expense. So now we have a model where we have Y, which is the sales, and two axes. Number one is the sales price. Number two is the advertising expense. Now, typically, before we run multiple linear regression models, since we have multiple axes, we do want to look at something called correlation matrix. And correlation matrix actually allows us to examine the relationship between Y and each of the X variables. And the idea here is that since we expect Y to be correlated with each of the X variables we consider, we do want to verify that by looking at the correlation coefficients. And if we put all of them together, it becomes a matrix. That's why we call correlation matrix. So right here is the correlation matrix that's provided by Minitab, where we can look at how the sales is correlated with the selling price and also the advertising expense. So this is how you read it. Starting from the first row here, which is the selling price, and look at the first column says weekly sales. So this number, negative 0.863, is the correlation coefficient between the two variables I just mentioned, which means selling price and weekly sales are negatively related with a correlation coefficient of negative 0.863. Now, if you recall from previous lectures, the correlation coefficient ranges between -1 and +1. The closer the number is to 0, then the weak the correlation is. So when the correlation coefficient is close to +1 or -1, that means these two variables are highly correlated. For this value, negative 0.863, I would say these two variables are highly correlated. Now there's another number right here, which is the correlation coefficient between advertising and weekly sales, which is 0.891, positive. So this tells me that the sales and advertising expense are positively related with a correlation coefficient of 0.89, which again tells me that these two variables are highly correlated as well. So that's good news because I do want to include advertising expenditure in my model. And if this variable is highly correlated with Y, then I made the right decision. The variable should be in the model. On the other hand, if in the future you look at correlation matrix, if one of the variables shows a small correlation coefficient, when I say small, I mean close to 0, then that actually indicates this variable may not be a good candidate for our X variable. There's one more number here, which is negative 0.654. And this is the correlation coefficient between advertising and selling price. These two are the X variables. Although at this point, when we run multiple linear regression model, before learning something called multicollinearity, This correlation coefficient is kind of less important as of right now. But I do want to give you a warning, that is, we will talk about something called multicollinearity. In that situation, and actually in all multiple regression analysis, this correlation coefficient is also important because we don't want the X variables to be highly correlated with each other. But just to give you a quick discussion here, when we see advertising and selling price to be negatively related, we do see that this value is not as strong as the other two correlation coefficients, which is good. These two X variables are correlated and they are negatively correlated. If you want to know why, or if you want to ask, does it make sense? I would say most likely yes, because when you have advertising campaigns, most likely you tend to have a sale and decrease the price of milk. So you can expect these two to be negatively correlated. The higher the advertising expense, the lower the price you tend to offer. So now I want to move to Minitab and show you how to obtain this correlation matrix. So now you should be able to see the Minitab screen that I'm sharing. I've already opened the data file, and the name of the file is called Mr. Bump Chapter 7. In this data file, you will see the three variables we need: weekly sales, selling price, and advertising. Now, first of all, to obtain the correlation matrix, we're gonna go to Stat and go to Basic Statistics, and then pick the correlation. It's right around here. Then inside the box for variables, we want to pick all three variables. You can pick one at a time, or you can push down the control key and check all three together. Then click select to select all three variables. And that's all we need. So click OK. The first one you see will be this scatter plot, which also shows the correlation coefficient. It's usually easier to look at this correlation matrix. We call this table the correlation matrix, and this is the same as we just saw on the PowerPoint. Okay, so now I'm gonna go back to the PowerPoint we were looking at. Let's move on to the next part, which is the estimation. Now we want to estimate the model. We want to find out the regression line that link the Y variable with both of the X variables. And of course, we're gonna use Minitab to do the estimation. What you see right now is on the right-hand side is what you will see in Minitab as the result. And I circled things that are important for us to know. We will go over everything you see here, but before that, I do want to move back to Minitab to show you how to get this output. Okay, so back in Minitab, to get the regression, you go to Stat and pick regression again, and choose fit regression model. It's really the same thing. The difference is that this time we're going to have multiple continuous predictors. So for responses, we pick weekly sales. For continuous predictors, we pick selling price and advertising. But since for every regression, we do want to check the residues to make sure all conditions are satisfied, you can also go to graphs and pick 4-in-1 to get the graphs of the residues, so that when you need to check the assumptions, we can do it right away. Click OK. So here we go. That's the regression output. At the beginning, you see the regression equation. Then you see a table called coefficients. That's a very important table. And the next table is the model summary, in which you can see the R-squares, which is also a very important measure for us. Analysis of variance. In Chapter 6, we didn't talk about it, but we do need this model for multiple linear regression, and we will talk about it. For the rest, these are the residual plots for us to check the assumptions, and we will go there later. That's how you get the regression analysis in Minitab. Once again, I'm going to move back to the file so that we can continue with the PowerPoint. Okay, so let's start from number 1, the equation and interpretation of the coefficients. So here's the regression line. It says weekly sales is equal to 16.41 minus 8.25 times the selling price plus 0.585 times the advertising. Now, if we eventually determine that the model is valid and good to use, we can use this equation to forecast the sales for any given combination of selling price and advertising, as long as they are in the range of our data. But before we use the model for forecast, we need to learn something and look at a few things. Number 1 is the interpretation of the coefficients. Looking at the first coefficient, which is negative 8.25, we kind of had a similar coefficient in chapter 6 when we look at the simple linear regression model. So interpretation for this number is similar, but with a very important condition. And I highlight that condition in bold. So the way we interpret this number is we say when price increased by 1 unit, which is $1 in our data, the sales will decrease by an average of 8.5 times 1,000 gallons. And by the way, our data is measured in thousands of gallons. Now, the big condition is that we want to hold advertising expenditure constant. So that's how we interpret the coefficient, okay? When we change one x variable, we do want to mention that we are holding the other x variable or all other x variables constant, and that is super important. We don't want to change all x variables at the same time. Similarly, the interpretation for the second coefficient, which is 0.858, is that when advertising expenditure increased by 1 unit, and which means it's $100, that's the unit in our data, sales will increase by an average of 0.59 times 1,000, which will be 590 gallons, holding price constant. So it's the same thing. If you want to change the other x variable, you want to hold the x variable, the first x variable constant. So that's how we interpret the coefficients. Now let's move on to the next part. After knowing how to interpret the coefficient, we're going to now talk about how to verify that our model is valid. And this is different from the way we did in chapter 6. In chapter 6, we test on the slope coefficient. And if we are able to verify that the slope coefficient is different from 0, significantly different from 0, we say the model is valid. That's not the case for multiple linear regression anymore. For multiple linear regression model, we actually look at the t-test to verify the validity of the model. So this is how we conduct the f-test. The idea of the f-test is that since we have multiple x variables in the model, we want to verify that not all of the coefficients are equal to 0. That's the idea. Think about it. If all of the betas, as listed here, are equal to 0, what would happen? So let me show you the model, the original population model right here. If beta 1, beta 2, beta 3, etc. until beta k are all equal to 0, then all the x variables will be dropped from the model. And this is very similar to the simple linear regression model case. If beta 1 is equal to 0, x is dropped from the model, then the model ends up with y equal to beta 0, which is a constant, plus the error term. And that means none of the x variables are related to y. So that means it doesn't make sense for us to estimate the model since it was useless, since the x variables are not useful or important in terms of predicting y at all. So that's the idea. That's the scenario we want to exclude using the f-test. And if we can verify that's not the case, which is the null hypothesis here, then we're good with the model. At least we can tell the model is valid. As you can recall for hypothesis test, when we have the null hypothesis, we usually have an alternative hypothesis. If not all the x variables are dropped from the model. Or in other words, if not all the beta are equal to 0, what's the alternative, right? So the alternative actually, it turns out to be the following. It says at least one beta is not equal to 0. Intuitively, if the null hypothesis says all beta is equal to 0, you might say, well, the alternative is that all of them are different from 0. Actually, that's not the case for this test. In addition, you can't require that alternative. And here's the reason. If we can verify that at least one beta is different from 0, then we're good. That means at least one x is highly correlated with y. At least one x will remain in the model. So worst case scenario with that is that we have one x variable in the model. It reduces to the simple linear regression model, which is still okay. Now, if you require all betas to be different from 0, you're basically asking all the x variables are significantly related to y. They're all useful in predicting y. Then going back to the selection process, recall that the x variables are selected by you or me or the researcher who are conducting the analysis, right? How can you guarantee that all the x variables you selected based on your intuition will be highly correlated with y, right? You can't. And that's actually the beauty of this multiple linear regression model. It allows you to include as many x variables as you want, but then eventually it will verify for you which x variables you selected are actually useful in predicting y. Okay, so with those hypotheses, the way we conduct the test that we are looking at the p-value. And the idea is that for small p-values, we reject the null hypothesis. How small the p-value should be? It should be less than alpha, which is 5%. And the p-value for this f-test is listed right here. Okay, so this is the analysis variance table I was talking about. You want to look at the p-value for regression, not anything else at the bottom. So we only look at the p-value for the regression, which is 0. And that's a good sign, meaning that we can reject the null hypothesis and claim that the model is valid. With that test and with this p-value, we actually can tell several things, not just saying the model is valid. We can also say that we now verify that at least one beta is different from 0. And furthermore, I didn't put it here, but now I do want to do that. So allow me to add something, which is number 4, meaning at least one x variable is significantly correlated with y, and at least one x is useful in predicting y. Okay? So that's something else you can say for this test as well. All right, so that's our test. Now we verified at least one variable, one x variable is important. And naturally, the next question is which x variable is important? We have 2 here. Are you telling me both or maybe one of them? Especially when we have multiple x variables like 5 or 10. You do not honestly expect all of them to be useful in predicting y, all of them to be highly correlated with y, but you do want to know which ones are highly correlated with y. And that goes to the t-test, which is used to track individual coefficient to see how each of the x variables are correlated with y. The t-test actually is very similar to the one we learned in chapter 6. The difference now is that we have more than one x variables and we have more than one p-value, but we do have one p-value associated with each of the x variables. So same as before, the null hypothesis is that the beta is equal to 0 and the alternative says the beta is different from 0. Since we're checking for individual coefficient, we do have this set of the hypothesis for each of the coefficient, which means for example, for selling price, right? We're checking beta 1 equal to 0 versus beta 1 different from 0. And to perform that test, we go to the corresponding p-value, which is 0.007 for the selling price. And we can tell this p-value is smaller than alpha, which is 0.05. Then that means good news for us. We are able to reject the null hypothesis, and we can claim that the x variable is significantly related to y. We also can say that this coefficient is significant or significantly different from 0. And the last thing we can say is that this variable is useful in predicting y. Okay, now moving to the next x variable, which is the advertising expenditure. Similar idea, now we're testing beta 2 equal to 0 versus beta 2 different from 0. And looking at the corresponding p-value, which is 0.003, we can tell again we want to reject the null hypothesis and claim that this x variable, advertising expenditure, is highly correlated with y and is useful in predicting y, which is the sales. And at the same time, we can say the coefficient is significant. Now remember, we talk about this concept of significant. When we say a coefficient is significant, we just mean that this coefficient is significantly different from 0. Okay, so that's the t-test. The next topic we want to look at is how well the model fits the data, the fitness. For the simple linear regression model case, we look at R-squared, right? If you recall, R-squared tells us the percentage of variation in the dependent variable that can be explained by the model or use the x variable. And R-squared ranges from 0 to 100%. The higher the percentage, the better the model fits the data. We have the same logic in multiple linear regression model. The difference is that we do not rely on the R-squared anymore for multiple linear regression model. Instead, we look at the adjusted R-squared, okay? And the reason being the R-squared can be inflated by the actual x variables we put in the model. So here's the idea. Now suppose I'm running regression models. For the same y variable, the same dependent variable, I have several choices. I can include just one x variable, or I can put 10 x variables in the model versus 5 x variables in the model. Of course, I'm talking about the same x variables, okay? Now, if I run the model, it turns out as I increase the number of x variables, the R-squared will increase with it. And it doesn't matter whether the x variables I add to the model is related to y or not. In other words, if I just pursue high R-squared, what I can do is to inflate that measure by adding 10 or 20 x variables, but they are useless. I can even use the random number generator to generate random numbers, put in the model, which apparently won't be useful in predicting y because they're just random numbers. But with that action, I am able to increase the R-squared. So it seems like it will give people this misperception saying that, the model with this extra 10x variables, which are random numbers, fits better for the data. So people realize that, and then the solution for it is to adjust R-squared. And the R-squared is adjusted for the number of x variables. To a certain extent, the adjusted R-squared penalize the model when you add too many x variables. The more x variables you have, the higher the penalty, because you need to take into account that when you add more x variables, you most of the time use important variables. Sometimes you are adding something that are not useful at all. So you are actually making the model less accurate. Okay, so that's the big change from simple linear regression model to multiple linear regression model. Now, for our case here, the adjusted R-squared is 91.25, which is not bad at all. But in comparison with the R-squared, it is 93.19. So apparently the R-squared is higher, and R-squared is always higher than the adjusted R-squared. That's for sure. The interpretation for the adjusted R-squared for this multiple linear regression model case is the same as before. We say after adjusting for the number of X variables, about 91.2% of the variation in sales can be explained by the model. That's the interpretation for the adjusted R-squared. Now we verified that the model is valid. We also learned how to interpret the coefficients. We also look at the fitness to model. The last step will be to check the residuals before using the model for forecast. And these are the graphs we use to check the residuals. We already obtained these graphs in Minitab, so I would not go back to Minitab. Let's just look at the graphs. Okay, the first two on the left side, they are used to check the normality of the residuals. For the situation we have here, by looking at the first graph, I would say the normality assumption is satisfied. The dots are not significantly deviated from the straight line. So I'm okay with that. But looking at this histogram, there's a little bit gap here that make it not nice. But I wouldn't say this is far from being normal. Now looking at the plot on the right-hand side up corner, this one allows us to check for heteroscedasticity, which means we want constant variance for the residuals. For this case, in my opinion, I would say that assumption is not violated. I would say the variance is constant, that is the range of the observations is not changing over time. Okay, so again, just to remind you, when we say this condition is violated, when we see a fan-shaped residual plot like these, and this is the line in the middle that represents the same line right there, then we say the condition is validated. We do see heteroscedasticity. Similarly, sometimes we may see situations like this. It's still fan-shaped, but it's the opposite way. In that case, we also say heteroscedasticity exists. That is, the condition is violated. For what we have here, I wouldn't label that as a fan shape, so we're good. And the last part allows us to check for serial correlation. The condition is that we require the residuals to be independent. We don't see any pattern. We want them to be random. By looking at this plot, I would say the residuals are random. I don't see a pattern of up and downs like this, or very neat pattern of up and downs like that. Okay, I don't see those. So that means these residuals are independent. I want to erase the red lines so that you can see it better. Okay, so look at these. They are random. Now we check the residuals. We determine the model is valid and all the conditions are satisfied. We are ready to do the forecast. And surprisingly, or maybe somehow you are disappointed, the forecast is just similar to what we did in chapter 6. And that's why I didn't show it here. And the reason being, in Minitab, what you do is you fill in the numbers for the two X variables, then you can forecast for the Y variables, which is the sales. One topic for this lecture is the dummy variables. So the dummy variable is actually a very useful tool for people to include other type of variables in regression. For example, sometimes we have categorical variables, which means the variable takes categories. It's not numbers. Like gender, color. For example, we ask students GPA. We may want to ask whether there's any difference between students at different classifications college. If we want to run a regression model to analyze that, then apparently in the model, we do need to incorporate classification. But you can't do it. In the data or in Minitab, you can't say, I'm going to put sophomore, junior, senior there. Minitab can't tell what you're trying to do. And that gives us the idea of including the dummy variables. So the dummy variables, as you can tell, dummy, which means just 0 and 1. It's like a switch on and switch off. Okay, and dummy variables are used to include categorical variables in the data in our regression analysis. The general idea for dummy variable is that when you have a variable that only have 2 categories, you need 1 dummy variable. But if you have 3 categories for your variable, you need 2 dummies. And for 4 categories, like the classification, you have 4 classifications, you only need 3 dummy variables. So in other words, you don't need 1 dummy variable to represent each category. You always need K-1 dummy variables. Category, apparently there's 1 category that will not have a dummy variable to represent it. We call that category the omitted category. Okay, I know the theory is kind of hard to understand what is going on. So I'm going to show you an example so that you have better idea about this dummy variable. Let's look at this. Suppose an analyst wishes to investigate how well a particular aptitude test predicts job performance. 8 women and 7 men have taken the test, which measures manual dexterity in using the hands with tiny objects. Each subject then went through a month of intensive training as an electronics assembler, followed by a month of actual assembly, during which his or her productivity was evaluated by the index having values ranging from 0 to 10. 0 means unproductive. In a scatter diagram, each female worker is represented by a 0 and each male by a 1. Now think about the variables we have and think about the data we're looking at. So the Y variable will be the performance rating. And the performance rating is measured by values from 0 to 10. We have 2 X variables. One X variable is the aptitude test score, in particular because we want to investigate how well this test can predict job performance. If you think behind the scene, it's most like that there are companies recruiting people to perform this type of job, electronic assembler job, right? And they want to recruit people who are good at it. And we do know that we all differ in different things, right? And instead of, every time asking the applicants to go on the line and actually assemble, you want to find an easier way or a more convenient way to predict how this person can perform the test. And maybe this aptitude test can predict it. So that's the idea. If the aptitude test can predict job performance, then that's easier for us to verify who are good candidates for the job. So that's one X variable. And the other X variable is the gender. And we include the gender is because sometimes gender matters. We all agree that men and women are not from the same planet. So apparently we differ in a lot of aspects. So gender matters. Now, if you want to include gender as the X variable, you need a way to incorporate that. So the way you incorporate that is to create this dummy variable. And here's how this dummy variable is created. This dummy variable, let's say, is x2. So we want x2 to take a value of 0 if this observation comes from a female. And we want this variable to take a value of 1 if this observation comes from a male. And that way we can differentiate between these 2 genders. Okay? And also look at the scatter plot. as mentioned in the question, zeros represent women and ones represent men. Apparently, at least in this diagram, we can tell in general, the zeros are higher than the ones. So that means in general, females have a better performance than men based on the same aptitude test score, right? And that also tells us it's very important that we control for gender. That means it's very important for us to differentiate between the two genders. Otherwise, if we mix it together, think about it. If we mix all of those together and don't care about the gender, then most likely if we fit a straight line regression, it will be somewhere in the middle, which is not very close to 0, not very close to 1. Instead, if we recognize that, you know what, there's difference in gender, if we can fit in 2 lines, one straight line for, let me show you, female, and one straight line for male, right? That would be better because these 2 lines represent each group, and the line for female is close to the female's observation. The line for male is close to the male's observation. That's the idea. So how do we do that? We label the first X variable as the test score, which is to a certain extent our main variable here. We create the dummy variable, which we label as X2. And again, as I mentioned, X2 takes a value of 0 for females, take a value of 1 for males. Then we can modify the original multiple linear regression model. Okay, so originally for multiple linear regression model in general, we have the following. Y is equal to beta 0 plus beta 1, x1 plus beta 2, x2. So when we have 2 x variables, right, if we want to fit in a multiple linear regression, this should be the model we're looking at. 2 x variables, beta 1 and beta 2 associated with each of the x variable. Now, since x2 is a dummy variable, takes only values of x1 and 0, we can further modify this model into 2 regression lines, and 1 for the female, 1 for the male. So if you compare these two, at the beginning, everything is the same. Y is equal to beta 0 plus beta 1 x1. Then, since x2 takes a value of 0 for female, so 0 times beta 2 means it's 0, it's gone in the model. Therefore, for the female, the model becomes y hat equal to b0 plus b1 x1. Of course, this is the estimated regression line. And then for male, x2 takes a value of 1, so 1 times beta 2 becomes beta 2. And that's why you see for the equation for male is y hat equal to b0 plus b1 x1 plus b2, because x2 is equal to 1. And that, if you arrange the terms, you get the following, which is another simple linear regression, which is another straight line. So now if you compare these two equations, you can tell that for female and male, they have the same slope, which is beta b1 or beta 1, the same slope, but the y-intercept is different, right? Y-intercept is different to represent the differences between the two genders. So if I pull back, right, you can see I have 2 lines, and I try to draw them with the same slope. We're gonna just have to assume that they have the same slope, but they do have different y-intercept, which is exactly what the model we have here tells us. Okay, so that's the idea of including the dummy variables. Now let's go to Minitab and see how we can estimate model with dummy variables. Actually, Minitab make it very easy for us. So let me switch to Minitab. The name of the file is called job performance. And in this file, you will see the y variable, which is performance, the two x variables, aptitude, I think, score, and gender. That must be a typo. And you notice that for gender, F stands for female and M stands for male. Okay. The nice thing about Minitab is that you don't need to code the categorical variable. Actually, in Excel, if you put F and M there, Excel will not allow you to run the regression. In Minitab, we're going to do the same as before. You go to Stat, Regression again, and pick Fit Regression Model. Now this time, the response variable is performance. And you will notice that we don't see gender there. But don't worry, when you go to continuous predictor, you want to put the aptitude score there. Now, once you click on the categorical predictors, you will see gender. This is because gender is considered to be categorical variable. It doesn't have a number. It only has words, right? The categories. And Minitab will automatically create this dummy variable behind the scene for you to verify, because Minitab will examine the data and determine how many categories there are and then generate the corresponding number of dummy variables. So I'm going to click OK to run the estimate. There we go. So Minitab tells you the dummy variable that was created using coding 1 and 0, which is the dummy, and also give you two regression lines, one for female, one for male. The rest are the same as before. We have the coefficients. That this gender M here is actually a very important message for us. Minitab will create the dummy variable for you, but you also need to know how the dummy variable is created, which is 1, which is 0, right? In our discussion before, we were saying 0 represents female, 1 represents male, but that's how we decide to do it. The question is it the same in Minitab? After all, we only tell Minitab F and M, right? And by looking at this, says gender, which means this is the variable for gender. M, that means in Minitab, for those observations with an M for gender, the dummy variable takes 1. And for those with an F for gender, the dummy variable takes 0. So actually it turns out the same way as we originally assigned the values. Okay. We can also see the R-square and analysis variance as before. All of these are useful for us to perform further analysis for the model to determine if the model is valid, if the coefficient is significant, if the assumptions are satisfied. So here I have the Minitab output for what we just had. One last comment I have is how to interpret the coefficient for gender. After all, it's a dummy variable, right? And this dummy variable represents male, meaning 1 for males, it takes the value of 1, for females, it takes value of 0. And the coefficient is negative 2.181. What does it mean? Well, since the dummy variable represents male and the coefficient is negative, that in general concept means male's performance is worse or less than female's performance. Okay, since it's negative. So again, since the dummy variable represents male and the coefficient is negative, that tells us the male's performance is less than the female's performance. Okay, now if we want to put the value in perspective, this negative 2.181 tells us that the job performance rating of males is lower than that of females by 2.18 units when holding the aptitude score constant. Or in other words, for the same aptitude score, and on average, males' performance is lower than females' performance by 2.18 units. So that's how we interpret it. And everything else is the same as before. If you look at the test of the f-test is here. The p-value for the f-test is 0, means the model is valid. If you look at the individual t-test, both p-values are 0. That means both coefficients are significantly different from 0. Both variables are important in predicting y. And that also actually verifies that it's very important for us to differentiate between the genders. The adjusted R-square is 90%, which is very good. Our Minitab output, we do have the residual output. All of the assumptions or conditions are satisfied. So the model is good for us to use.